Great. So we're going to talk about comparison first. All right, with comparison, you need a control group, right? Because control groups provide baseline data for comparing the effects of the treatment. I can't figure out if the treatment works unless I have something to compare it to. So depending on the purpose of the experiment, control group may be given an inactive treatment, which would be a placebo, an active treatment that currently is on the market, or no treatment at all. So here's our example. In an experiment in which blood pressure medication is tested, one group is given the blood pressure medication while the control group is given a placebo, right? So you're comparing the effects of the group with the placebo with the effects of the control group, right? I'm sorry, with the effects of the blood pressure medication group. All right, so here are our main ideas with comparison. Number one, the control group and the experimental group are compared against each other. The only difference between these two groups is that the independent variable is changed, right? The only difference should be that the independent variable is changed. So the example with the caffeine is the only thing changing from each group. The sugar level was kept constant, right? The independent variables controlled or held constant in the control group, meaning that we had no caffeine in the control group. All right, a single experiment may include multiple experimental groups, which all may be compared against the control group. All right, so that just means we might have more than one treatment group, right? We could have 6 different treatment groups in one control group, and we'll go through some examples with those in a minute. The purpose of having control is to rule out other factors which might influence the results of the experiment. Again, going back to the results of the caffeine experiment, we ruled out sugar because we kept sugar constant in both, right? So not all experiments include a control group, but those that do are called controlled experiments. A placebo may also be used in the experiment. A placebo is not a substitute for the control group because subjects exposed to the placebo may experience effects from the belief that they are being tested, right? So in the example where I gave out the Coca-Cola, I would cover up which labels had caffeine and which didn't, so that both groups did not know whether or not they were getting the caffeinated drink. All right, go ahead and flip the page over. All right, control groups can be subdivided into the following types. Now, this is from the FDA, the Food and Drug Administration. So these are different types of control groups that you can use when you're testing food and drugs. Placebo concurrent control. That's one group is given the treatment, the other a placebo. Dose comparison, right? Where you're comparing 2 different doses, right? So in every single one of these examples, you have comparison, right? You're comparing, number 1, the treatment to number 2, the placebo. You have 2 different doses here. Number 1, first dose. Number 2, second dose, right? So you're comparing those 2. No treatment. So you've got one group is given the treatment and the other is given nothing, right? So you're comparing the treatment to nothing. Active treatment, concurrent control. You've got one group is given the treatment and the other is given an existing therapy known to be effective, right? So if we're talking about blood pressure medication, we might be doing giving one the blood pressure medication and the other group might just be changing their diet because we know that's effective, right? So we're comparing the results of the pill to changing our diet. And historical control, one group exists experimentally, right? The control group is compiled from historical data. So I'm comparing historical data to the experiment results. So in every single one of these examples, you're comparing one to the other. All right, example 1, Justin usually blows his nose using Kleenex tissues. His snot keeps leaking through the tissue. He decided he is going to create an experiment to find out if there is something better. What is his control group? All right, so what does he usually use? What's his historic context, right? He wants to see if there's something better than what? He usually blows his nose using Kleenex tissues. So he's going to create an experiment to find out if there's better tissues out there, right? So your control group would be Kleenex, which you already use. All right. Go ahead and pause the video, try example 2 on your own. Okay, so we have lots going on in this example, right? So let's start off with identifying our explanatory and our response. All right, they want to study the effect of different materials on the melting rate of ice, right? So our explanatory is material. I didn't give myself enough room. And the response is the melting rate. All right, they placed pieces of ice onto trays. Group 1 was covered in plastic, Group 2 covered in paper, Group 3 covered in aluminum, and Group 4 remained uncovered. All right, so what is my control group here? Control is the uncovered. How many treatments do I have? I have 3 different treatments. Treatment 1, covered in plastic. Treatment 2, covered in paper. And treatment 3, covered in aluminum. And you're comparing each of these melting rates with the uncovered, the control group. So I'm comparing plastic with uncovered, paper with uncovered, aluminum with uncovered. So our big takeaway with comparison is that control groups provide a baseline data used for comparison. So you need to have a control group, to use for comparison, right? Okay, part 2, random assignment. So random assignment. Experimental units are assigned to treatments using a chance process. So a chance process cannot be assigning the first 10 units to treatment 1 and the second 10 units to treatment 2. It has to be a truly chance process. And by doing that, you can only use things that are like a random number generator, a random number table. If you've got 2 treatments, then you can flip a coin, right? But that's only if you have 2 groups. If you have more than 2 groups, you're going to need to do a random number generator or a random table. Now what you would do is label every single experimental unit a number 1 through whatever, and then use a random number table like we did last packet, or a random number generator to assign to treatment 1, treatment 2, treatment 3, and so on. All right, here's our example. You are studying test-taking behaviors of a college of 5,000 students. You choose every 50th student from a list to create a sample of 50 students to study. Is that random assignment? Yes. And specifically, it's systematic random assignment. Now, if you have a list of 50, you can't go straight down that list, right? It might be alphabetical. To be truly random, you're going to pick a random person to start with and then select every 50th student. All right, our non-example. From the same list of 5,000 students, you randomly circle 50 names. That's not good enough for random assignment. You cannot use that. It's not truly random because your biases, known or unknown, could affect who you circle. So you might unknowingly circle boys' names over girls' names, American-sounding names over foreign-sounding names, short names over long names. You just never know. Biases are inherent in all of us, which is why a random number generator or a random table will give us a truly random assignment. So you cannot have random assignment without a chance process. All right? Why would a researcher randomly assign participants to conditions? All right, why do we need random assignment? Why is it important? Well, random assignment can allow researchers to make casual conclusions about the effect of one variable on another. We'll get to that in a second. Random assignment allows the researchers to rule out explanations based on personality and individual difference variables. So if I take it all the way back to that caffeine example, didn't we say that individual difference variables would make a difference, specifically caffeine tolerance in our subjects? So remember in our example with the caffeinated drinks, some of my subjects had caffeine tolerance, which would affect their heart rate, right? But if I'm doing random assignment, then randomly I should have equivalent groups that contain both people that have caffeine tolerance in both groups. So that allows me to control for that. Random assignment makes it equally likely that a person with a certain characteristic is in each condition of the experiment. So my caffeine tolerant subjects would be randomly assigned to treatment and control. If they all end up in one group, that's bad for my experiment, right? Because I can't draw a conclusion about the effect of one variable on another because the caffeine tolerance is affecting the result. So random assignment creates roughly equivalent groups by balancing variables. So I balanced my caffeine tolerant people into two separate groups. All right, so a researcher wants to randomly assign participants to a treatment and control group. Which of the following approaches ensures the treatment assignment is random? Flipping a coin, assigning treatment by gender, obtaining nationally representative samples for both, or assigning treatment based on who needs it the most. I hope you selected A. That's my only truly random, right? By gender, those are individual characteristics between men and women that might affect the experiment. Obtaining a nationally representative sample makes sense when you're trying to draw a conclusion to a specific sample, but it doesn't talk about random assignment at all. So let's eliminate that. And then assigning the treatment based on who needs it most. All right, well, that might be morally ethical, but we're talking about random assignment, right? So I can't go based on who needs it the most. That might affect my experimental results. All right, so our big takeaway so far, we had comparison, right? And with comparison, we said control groups allow for baseline data to compare. And then here, random assignment, we need it to create roughly equivalent groups by balancing other variables. And random assignment means a chance process. Okay? Part 3, control. All right, control is controlling for other variables. Controlling for other variables that may impact the experiment. So keeping all variables constant for all experimental units. So my example here was the sugar content in caffeine, Coca-Cola, and decaf Coca-Cola. The sugar needs to be the same in both, right? That way I control for the sugar and I say that the sugar did not make a difference because it was the same for both groups. What really made a difference was the caffeine. All right, placebo effect describes the fact that some subjects in an experiment will respond favorably to any treatment, even an inactive treatment. All right, now Ms. King is going to show you a video later that really illustrates the placebo effect. For now, in the caffeine experiment, we'll say that our placebo was the decaf Coke. So basically, everybody in the room was drinking Coca-Cola, right? They didn't know if it was caffeinated or decaf. And so if there was some sort of placebo effect where they believed they were drinking caffeine, so therefore they were more alert and their heart rate went up, then it went up for everybody. We controlled for the placebo effect because no one knows if they're getting caffeine or not. Which leads me into blinding. So I've got single blind and double blind. So a single blind, either the subjects don't know which treatment they're receiving, or the people who interact with them don't know. Someone doesn't know. That's why it's single blind, right? Now this would be important because if I gave out a Coca-Cola to every student in the room and it was very apparent which ones were caffeinated and which ones weren't, then I wouldn't be controlling for my placebo effect, right? The ones drinking caffeine might feel more energized and their heart rate might go up as a result of this placebo effect. So a single blind, either the subjects don't know which treatment they're getting, treatment or control, or the people interacting with the subjects passing out the drinks don't know. All right, so here's my example. Researchers are doing a study to determine if certain types of medication cause people to feel more alert. Participants knew that the researchers were testing a hypothesis. They might start acting more alert after ingesting the medication, right? If you use a single blind procedure and you don't tell the participants what you're looking for, the people in the study are less likely to inadvertently bias the results. Inadvertently means not on purpose, right? People aren't acting differently on purpose. It's just a mental thing. All right, now double blind. Neither the subjects nor those who interact with them measure the response variable, know which treatment a subject receives. So imagine that researchers want to determine if consuming energy bars before a demanding performance lead to an improvement in the performance, right? So participants are, let's see, I'm running out of time on my video, so keep reading and we'll pick up next video.